So how about your board plot experience? Hello,
Yes, sir.
how is your feelings about board plot now? Is it okay?
Yes, sir.
Alhamdulillah. Okay, very good. So basically today we will discuss an important application of the operational amplifier. One of the important application is filter, Do you heard about the filter before?
Yes, sir.
What is filter?
So it only allows certain part of the frequency range.
Yes, and the rest of the frequency will reject.
Yes, sir.
Okay. So how the filter consists and what are the elements involved in the filter? Do you remember?
RLC.
RLC. So that RLC based filter usually called the passive filter because all these R, L and C are passive element. Is it or not? R, L. Can you see the white screen? Hello?
Yes, sir. Yes, sir. You can see.
So that RLC based filter is basically called the passive filter because all the R, L and C are the passive elements. So this is not our concern now. Our concern is the active filter basically. The filter is the same characteristics. Whenever it is passive or active, it doesn't matter. But there are difference in between as a use of the component. So basically, since the RLC based filter is called passive filter because of the RLC component or passive component. On the other hand, we will say active filter. So what will be the active filter then? According to the name, we should say that the active filter should include active component. Is it or not? Since the passive filter are based on the passive component, then active filter should involve with the active component. So what are the active component? Do you know what are the active components? By inductors or capacitors তো এখানেই আছে.
Sir,
Exactly, op-amp, or you can say specifically the transistor. The transistor, because op-amp is basically based on the transistor. So transistor is also active component. So op-amp based filter is basically the active filter. So we will see the active filter. The active filter basically is almost same like the passive filter instead of the use of the operational amplifier. Okay. Okay, so this topic, a part of the topic will be covered from the Sadiku book, chapter 14, article number chapter 14.8. Okay, 14.8 is active filter. So why should we need the active filter? The first question, because there are very specifically we can say that there are three major limitations to the passive filter considered in the previous discussion or earlier discussion. First of all, they cannot generate gain greater than unity. So gain is always unity for the passive one. Okay. So since the gain is unity, then passive elements cannot add energy to the network. And the secondly, the passive filter require bulky and expensive inductor. Inductor is very large, or sometimes it's very expensive, large and expensive inductor. And thirdly, the passive filter perform poorly at frequency below the audio frequency. I mean, at low frequency, its performance is very poor. At low frequency, performance is very poor. So these three major limitation happened in the passive filter. Then we have to see these three limitation can overcome by the active filter or not. Most of them are overcome by the active filter, because the active filter consists of the combination of resistor and capacitor with the op amp. Okay, and almost all the advantage of the passive filters are getting from the operational amplifier. And first of all, the active filter is oftenly smaller and less expensive, because there are no inductor in the active filter. No inductor, no inductor in the active filter. And because there are no inductor, since it is only based on RC circuit, it is also easy to realize with the integrated circuit of the filter. And secondly, the active filter can provide amplifier gain in addition with the providing the same frequency response of the RLC filter. So it has gain, gain greater than unity. And thirdly, the active filters can be combined with the buffer amplifier or voltage follower. And we already know that the voltage follower will be isolate each stage of the filter from source and load impedance effect. So that will be also reduce the loading effect, or eliminate the loading effect. Earlier we have seen that how we can use the buffer circuit. So it can be reduce the loading effect. Okay. So these are the advantage of the active filters. Okay. And now basically the filter is the, but there is one limitation of the active filter. The practical limit of the most active filter is about only 100 kilohertz. The most active filters operate below than the frequency. So one of the limitation is only 100 kilohertz. 100 kilohertz is the maximum limit of the frequency to perform well. So this is one limitation. So based on this, we will basically, in terms of the specification, or in order to fulfill the requirement, we should think that which type of filter actually we need to design. Then this RLC based passive filter and op amp based active filter, excluded these two types, there are another kind of filter. Basically, this is usually not discussion in during this, but you can keep in your mind that another kind of passive filter also used in high frequency, because you see the RLC can applicable in high frequency, but it has the limitation this one, and active filter can overcome this limitation, but it cannot apply in the high frequency. Then how we can filtering in the very high frequency? That's why in very high frequency, there is another passive filter is called distributed parameter passive filter. So that one is not of our concern. Okay, but you just keep in your mind that another kind of filter is also available. Okay, so the filter can be classified according to their order. What is the order? Order is nothing but the number of pole. What we have discussed earlier, the transfer function. From the transfer function, we have seen that on transfer function can include one or more number of poles. So the number of poles will be determined the order of the filter. You can keep in your mind that the order of filter can be determined by the number of pole. So first we will discuss first order, all types of first order. Another, based on the pass band, we can classify it also the filter as a low pass, high pass, band pass, and band reject. Is it or not?
Yes, sir.
By the characteristics of the filter, we can classify it by low pass, high pass, band pass, and band reject. But by the order of the number of pole, also we can classify it that first order, second order, third order, or even higher. And also there are some other types of filter as well. So first of all, we can see the first order filter. If we simply design a inverting amplifier, that can be represented by first order filter. You know what we have discussed earlier during chapter 9. Most of the part will be repeating. The most of the analysis and the calculation is almost similar. So if we consider a in generalized inverting amplifier, what we have discussed earlier during the application of the op amp, we can repeat again. You see a generalized inverting amplifier. If is impedance, input impedance and feedback impedance ZF. This is output and is B input. What is this? Hello. We can say this is a simple inverter operational amplifier. Is it or not?
Yes, sir.
Yes, sir. Yes, sir.
So depends on the input impedance and output feedback impedance, we can perform that the first order low pass or high pass. If you consider that Zi, if Zi replaced by Ri, suppose Ri and ZF replaced by a parallel circuit of RC. This is RF and CF. Then it will perform like a low pass. Low pass. And if Z replaced by a series RC, RC and ZF replaced by simple RF, then it will be performing as a high pass. It's very common circuit we have discussed earlier. And if we consider our previous discussion, we can also find out the transfer function. The transfer function is what? H omega. H omega is B naught by Bi, which is minus Zf by Zi. From our previous inverting amplifier discussion, we know that feedback resistance by input impedance. So it will be, if you simplify it, you will have H omega is equals to minus Rf by Ri into 1 over 1 plus J omega Cf Rf. Cf Rf. And also you can find the corner frequency omega c. How we can find the corner frequency? Can anyone say? Corner frequency, or you can say it is the breakdown frequency, or you can say the block frequency, or also cutoff frequency. Even you can say it is 3 dB frequency. So how we can find out this 3 dB frequency omega c, the cutoff frequency? Can anyone say? Hello? Hello? At corner frequency, what about the magnitude? Huh? Hello?
The
Can you hear?
maximum.
Yes. During the board plot analysis, we have seen that at the corner frequency, the magnitude is equals to √2, is it? কি ভাই আরেকটা পড়তেছি কি আগেরটা ভুলে গেলে হবে? It was √2 and corresponding value is about 3 dB. So if we calculate the magnitude of this one, and if we put magnitude equals to this one, √2, then we can find that the cutoff frequency omega c is equals to 1 over Rf Cf. And this is for the low pass. Similarly, if you consider this one, you will have the transfer function like this. It will be minus J omega Ci Rf one plus J omega Ci Ri. And the cutoff frequency omega c is equals to 1 over Ri Ci. Ri Ci. So this two is called first order FRIST, first order low pass filter, if you consider this one, and this is first order high pass filter, if you consider this one. And based on this first order low pass and high pass, we can construct the first order band pass filter. The first order band pass filter will be band pass filter the first order band pass filter may be combined with that from a by cascading a unity gain low pass filter. Okay, a unity gain low pass filter, a unity gain high pass filter, and an inverter with gain of minus Rf by Ri. How we can construct a low pass filter with unity gain? low pass filter with unity gain, and then a low pass filter, a unity gain high pass filter with unity gain. If we pass the signal from the unity gain low pass filter, then pass from the high pass filter unity gain, and then if we pass this signal through inverter, so we will have the passband filter. Output will be the passband filter, and the corresponding transfer characteristics will look like this one. Usually, if it is omega, it is omega, and the corresponding 3 dB frequency or cutoff frequency, lower side is called omega L, and upper side is basically omega H, and this portion is called bandwidth, usually B, bandwidth. And also there is a center frequency, we say center frequency denoted by omega naught, and corresponding this value, if you consider that the value of this one is K, then the corresponding 3 dB will be 0.707 K. The value is sometimes called the 3 dB value or half power point value, the magnitude. Okay. This is corresponds to 0, and this is basically the H magnitude. So approximately the output of the band pass filter is look like this one. So if you construct based on the low pass, high pass, and the inverter circuit, the circuit will be look like this one. The low pass filter, this is the low pass section, is R and C1, and then we should have the high pass section is R C2, then after high pass section we should have the inverter, so it will have the input impedance is RF by RI. This will be the output, B output. It can be grounded, and this will be input. So basically it has 3 stages, the first stage and the second stage and the third stage. The stage one is low pass filter. It is low pass filter, and from this low pass filter we will have the value of omega H. And then is stage 2 is the high pass filter, and from the high pass filter section we will get the corner frequency of omega L. And then stage 3 is the inverter section, from which we will get the gain. because it's a simple inverter circuit, is it? And the gain we can easily find from the gain here. So this is how we can get the first order band pass filter. First order band pass filter. And in case of this is a cascading circuit, we can add 3 stages together. So how we can calculate the transfer function? In case of operational amplifier, if we cascaded the circuit, then we can simply multiply the gain of each section. The gain of each section. So each omega, it will be equals to V naught by Vi. So it will be multiplication of gain of each of the section. So the gain of each section is 1 over 1 plus 1 over 1 plus j omega C1R is the gain of first section. Then multiplied by gain of second section is j omega C2R by 1 plus j omega C2R. J omega C2R. And then the gain of the last stage is minus RF by RI. So this will be the transfer function of the first order low pass band pass filter. First order band pass filter. Similarly, based on this first order low pass and first order band pass, we can design the first order band reject filter. First order band reject or band stop filter. Band reject or band stop. Band reject. So from the name itself, we can get an idea that band reject, meaning using this filter we can reject a certain band of frequency, and the rest of the frequency will be passing through it. So it's simply inverse like the band pass filter. Simply inverse like the band pass filter. So we can construct the band reject filter based on the low pass filter, high pass filter, and with a summing amplifier. So it will be look like this one. You can have a low pass filter, which will determine the omega L, and you have the high pass filter, which will determine the omega H, and then if we connect these two, provide the input Vi, and then we will pass it through the summing amplifier. Yes, a summing amplifier. Then it will perform like a band reject filter. If it is V1, it is V2, then the output will be V naught equals to V1 plus V2. And its corresponding transfer function will be look like just inverse of band pass filter. If you have the omega H here, then the transfer function is look like this one. So if you have the 3 dB one is like this. So this will be omega L, this is omega H, and you should have the center frequency omega naught. and the stop band is this one, B, and pass band is rest of this. And if it is K, then the corresponding value of this one is 0.707 K, the 3 dB magnitude. And similarly, from this one, we can calculate the transfer function omega, H omega. H omega is, since this is a summing amplifier, so from the summing amplifier, we know that it will be, okay, if we draw the circuit first. If we draw the circuit first, so you will have a low pass section. Low pass is so you will have a low pass. Low pass is a resistor, capacitor. Low pass, and you will high pass is then you have combined these two and provide the input. And minus plus, we have the ground. Through these two, and then you will put this one in the summing amplifier, inverting summing amplifier. Inverting summing amplifier. This is your output. This is your output VI. So it is R, it is R, it is R, it is C1, it is C2, it is R, it is RI and RI. It is your RF. So since it is a summing amplifier, we can have our transfer function like this way. Simple H omega. H omega is equals to minus RF by RI and addition of the input. Addition of the input is 1 over 1 plus j omega C1R of is R only minus j omega C2R divided by 1 plus j omega C2R. So this will be the transfer function of the first order band reject filter. So basically all these circuits are based on the two important circuits what we have earlier discussed during the frequency response. We can repeat some of the portion from chapter 15 of the Newman book. Chapter 15 of the Newman books. Chapter 15. Okay. So basically an important application of the op-amp amplifier is the active filter, and the word filter refers to, okay, we know this one. Okay. Okay. So if we summarize the advantage of the active filter, we can say that the maximum gain or the maximum value of the transfer function can be greater than unity, and the loading effect is minimal, which means that, compared to the passive filter, we can eliminate the loading effect. If we consider the two previous simple RC circuit, what we have earlier discussed during the frequency response, the two RC circuit, one of them was like this. There is a C output and input, ground. It was VI and B input. And another circuit was just replica of this one, R C. Is C R R C is B output and B input, and its corresponding transfer function was like this one. If it is omega or phi, this T is a omega. If it is omega, then it look like this one. It was like unity. So basically, if you mark here, it is FL, and this is basically the pass band. And this portion was stop band. Stop band. And this one corresponding is low pass, is like this one. T J omega. Is like a unity. So if you draw a line, so it and is stop band, and it is the pass band. We have seen these characteristics earlier. Huh?
Yes, sir.
And also, on interesting thing, we slope of this one. Also we have seen it is that is about 20 dB per decade. Is it or not?
Yes,
And
sir.
simply in first order, we have seen that is 20 dB per decade, or maybe we can say that is 6 dB per octave. 6 dB per octave or 20 dB per decade. So in most of the cases of the active filter, one of the important specifications are given is this one, and this one is usually called the roll off. Term is roll off. So this roll off will be more closer if your number of pole is increasing. Number of pole is increasing, meaning if your filter order is higher. If your order of the filter is more higher, then the slope of that roll off will be more sharper or more steeper. Okay. Okay, then this is on this case is happened for unity gain because of the passive filter. So if we incorporate a simple voltage buffer or buffer circuit, then we can get the active filter, you know. So how we can get we can make. Okay, so in this case we have calculated the transfer function. What was the transfer function? Ts, it was about src by 1 plus src. So it has a single pole. Single poles means a first order filter. And in this case also the Ts was 1 over 1 plus src. So this is also a single pole. So single pole means it's a first order filter. First order filter. But since still we didn't use any op amp here or here, so it is a simple passive filter. But if we add the operational amplifier, then it will convert it into active filter. We can see how we can make it active. If we simply just we put a voltage buffer like the if we simply put a voltage follower or voltage buffer V naught, then it will perform like a active filter and without a loading effect, without any loading effect. As simple as it, very simple. But still this is first order. This is all are first order. Uh, order first order filter. Okay. You know, one interesting thing, if we do not use this one, the voltage buffer here, then if we take any output in this section, what will happen? The center frequency can be changed, the operating frequency can be changed, and also depends on the load, the gain is also will be changed. So if we use this voltage follower in both the cases, then the center frequency, the operating frequency, and the voltage gain, nothing will be changed. So this is one of the important advantage of the active filter or operational amplifier based filter, you know. But since all is the first order filter, all are the first order filter. And the roll off is basically is 6 dB per decade or 20 dB per decade. Sorry, this is not decade, this is octave. Octave, and this is decade. So if we need more sharper like this or like this, then we need to increase the number of pole. Increase the number of pole. So increase the number of pole means basically we need to increase the number of capacitor. Later on we will see that if we increase the number of capacitor in the circuit, then that will be increase the number of pole, and increase the number of pole will increase the roll off of the decade line, slope of the straight line. And it is one of the important specification which is given for the active filter, you know. Okay, so that's all about the first order, low pass, high pass, band pass, and band reject filter. Any questions so far?
Sir, in the band reject filter, don't we use the high pass and low pass filters of unity gain?
Yes, yes, of
Yes.
course. In the band reject, we will use the low pass, high pass, and then we will pass it through the summing amplifier. Whereas the same low pass and high pass filter, if we use in a series connection, and then if we provide the output of the high pass filter to the inverter, that will behave like a band pass filter. This is more common first order low pass, high pass, band pass, and band reject. But later we will see the some other kind of a higher order filter. There are a lot of types of filter basically. So what I discussed today, only the first order, low pass, high pass, band pass, and band reject. And tomorrow we'll discuss about the higher order of the filter and also the generalized form of the filter. 2 pole, 3 pole, 4 pole, or more than this.
Sir.
Yes, please.
Sir, মিডে কি স্যার আমাদের ইন্টিগ্রেটেড সার্কিট ডিফারেন্সিয়েটেড সার্কিট ওগুলো থাকবে স্যার?
কোনটা চ্যাপ্টার 9 থেকে বলছো?
ইয়েস স্যার, ইয়েস স্যার।
থাকতেই পারে। তুমি what you can do, you can analyze all the circuits, because what I feel that in terms of analysis, if you remember the ideal characteristics of the operational amplifier, then you can analyze any circuit, is it or not? And in order to increase your confidence, what you can do, you can analyze all kind of circuits so that you can keep in your mind the parameter what you need to assume in what cases. Number one, you should clear yourself about the virtual short and virtual ground. Okay, virtual short and virtual ground. Then also you need to know that the input of the operational amplifier, the input terminal of the operational amplifier is equal voltage. The small V1 and V2 is always equal. Okay, and also there will be no current entering to the op amp. I mean the entering current of the operational amplifier is always 0, because we consider that the input impedance of the operational amplifier is infinite. So there will be no current passing through the operational amplifier. And also the output impedance of the operational amplifier tends to 0. So if you keep in your mind these 3-4 things, then I think all the circuit is basically based on your previous circuit analysis knowledge. Is it or not? Anything else? Can you tell me?
স্যার কিছু টপিক যেমন স্যার একটু স্যার যেমন ওই যে কারেন্ট সোর্স কনভার্সন, তারপরে স্যার ওই
কোনটা কারেন্ট টু ভোল্টেজ কনভার্টার,
কারেন্ট টু ইয়েস স্যার ওটা কি স্যার পড়া লাগবে?
এই কোনটা পড়া লাগবে এরকম আমি তো মনে হয় বাদ রাখছি না কিছু। হ্যাঁ, বাদ রাখছি নাকি কিছু?
স্যার ওই অ্যাপ্লিকেশনের মধ্যে থেকে স্যার মনে হয় স্যার ওই যে কিছু
হ্যাঁ, এখন তোমার এই সবগুলো পড়াইতে গেলে তো টপিক সব কভার করতে পারবো না, হয় এই কারণে হয়তো কিছু জিনিস আমি ছেড়ে গেছি, বুঝছো?
আচ্ছা, মিডের জন্য স্যার ওগুলো পড়তে হবে।
Still I am going with laggings, but I make you sure that if you understand what I have discussed during the class, then you can answer all the questions. I can make sure you. If you understand the things what we have discussed during our class period, then you can answer any question, inshallah.
Yes.
Okay, then maybe tomorrow we will discuss about further on the active filter for higher order, 2-pole, 3-pole with the generalized form. Huh? Okay.
Yes, sir. Assalamu alaikum, sir.
কে পরে আসছিল বলো তো, কেউ আছে?
Sir. Sir.
ID please.
140.
140.
But I have. Yes,
you already given, eh?
Yeah, no, I don't ask for attendance. I ask for mid-syllabus. Mid-syllabus.
Mid-syllabus.
Yeah.
Tomorrow we will conclude our mid-syllabus, inshallah.
Okay.
Did you receive the course outline?
Yeah.
So inshallah by tomorrow we will conclude our discussion, if possible. If not, then maybe half hour or 1 hour we will take on Sunday after quiz. Okay. Hello.
Yes, sir.
Is it okay?
Yes, sir.
Okay. But I will try to conclude tomorrow, inshallah.
So 49.
40?
49.
Ali Alushan Kamara.
Yes, sir.
Kamara. Okay, anyone left?
Say 142.
140.
42.
Yeah, you have already given, I think. I take your attendance earlier. I already given. So who responds for you? Huh?
I was the one, sir. I think like you didn't hear me, that's why.
No. If you respond, I should.
Okay.
Okay. And on 39, Jamaluddin in chat box is also done. Okay. Okay, then see you tomorrow, inshallah.
Assalamu alaikum, sir.
Assalamu alaikum.